Welcome friends to the second session of marketing research and analysis. In this session we will be continuing with the non-parametric test. Earlier we had done with some of the non-parametric tests like the Kruskal Wallis test, which is a similar kind of test as like the ANOVA in parametric test, and then we did the Mann-Whitney U test, which is similar to the independent sample t test of a parametric test. Then we also did in the last lecture we did the runs test, right. The runs test is a test in which we try to check the number of the occurrence of an event, right, and whether it is random or non-random, right. So, today we will continue with some of the more non-parametric tests, and we will see how they can be useful for any researcher, and they can be even quoted in referred to in some kind of journals, publications and in academic work. Okay. So, runs test, just to brief, I have just kept this one slide. So, the runs test in the sign test which we did was to measure was a measure to test the randomness of a dichotomous variable. So, in the runs test we tested what is the randomness. So, if it is random or if it is non-random, accordingly we can decide what action needs to be taken, and this is especially true or more useful in case of a quality control check. So, this test is conducted by determining whether the order of sequence in observations are obtained is random or non-random, right. Okay. As I said, this it is used in quality control situations and helps in detecting whether the variation in quality is systematic or random, and accordingly take necessary action. On the other hand, we said sign test, which I had also said at that time, I have been repeating, is not a very powerful test, but is a test for examining the differences in the location of two populations based on the paired observations, that compares only the sign of the differences between the pairs of variables without taking into account the ranks. So, what is the rank? That is not that is immaterial to us, rather we would only say whether it is bigger or smaller, greater or lesser, that is all, right. And according to the number of signs, the number of greater value or the number of lesser value will decide whether the hypothesis is true or not true. Okay. So, these two tests we had done, right. What we can do is I am thinking of showing you to how to do this one of these tests in the SPSS. So, this is the runs test which I wanted to show you. So, this is, if you can see, this is the data in which if you can go to the variable view. So, the quality of item is being measured, right. So, if it is the quality of item, if you go, if it is 1, if we say it is a good item, right, and if it is 0, let us say it is a defective item. So, this is how there has been about 40 such samples have been taken, and the first item was a good one, second, third was defective, 1 is the defective and no defect is 0 actually, right. So, 2 no defects, then again a defective, then 5 no defect, then 3 defective, then again good, then defective, then good, then defective series, then good, it goes on, right. So, now we want to see whether this is what is the hypothesis, there is no it is a random occurrence. So, the occurrence of the defective or the non-defective item is random in nature. So, let us run the test on the SPSS. So, if you go to analyze, go to non-parametric tests, and here you have you can see one sample, independent sample, related samples, and you go to legacy dialogues. Here you will see there are different again examples of chi-square, binomial, the runs test. Now, we want this runs test, right. So, we will take this variable into here. As you know, this is a nominal variable, so it is 1 or 0, so defective or not defective. Now, this mean median mode, if you see, now if you remember, in the case of a non-parametric test, the value that we use is often the median, right. But if the data or the value, if the test is a parametric test or a normally distributed, the reference is always the mean, right. So, but here we will take the custom point as something which we want to as a cutoff value. Now, what is the cutoff value? A value in between 1 and 0 here in this case. So, what I am doing is I am taking a value of, let us say which is 50% between, so 0.5. So, 0.5. Okay. So, okay. So, I will take this, and what are the options? I will take just the descriptives to see what is happening, right. So, okay. Now, if you look at it, now if you look at the descriptive statistics, the quality of item n is 0, the mean is 0.43, but although it makes hardly any sense, deviation is 0.501, minimum and maximum is this much. Now, look at the runs test, the table. Now, what it is saying, the test value is 0.5, which we had kept as the cutoff mark, the total number of cases is 40, the number of runs is 16. Now, how did this come? You have already done it, just to remind. So, 1, then here 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, you can go add and it will be 16, right. But suppose let us say and if you see the output again, now let us see the output with now what is saying, the number, the z is minus 1.3828 and the significance value is 0.184. So, since we have a value of, generally we take the 5% level or the 10% maximum, it is taking, it is a much higher value than 0.05 or 0.01. Right. So, in such a condition we will say that so 0.1. So, we will say that this, since this value, the significance value is much higher than that. So, the null hypothesis is to be not rejected and rather it should be accepted, right. So, that means what is the null hypothesis? That there is the occurrence is random in nature, right. But suppose, but that is not what the researcher is interested. You can just change the data a bit and see, by suppose what I will do is I will reduce the number of the occurrences. So, what did I say? If the number of occurrences is too few or the number of occurrences is too large, then the randomness is the systematic error becomes larger in role than the randomness. So, let me show you an example. Let us take this case. What we will do is, instead of so I will this one I will make it 0, right. So, this is 0. So, so I will put in more number of zeros a bit, right. So, this is, let us say this is again a 0, right, this is a 0, right, and let me see if we take little more, this is 0, this is, so I can put it 0, right. So, now let us rerun this, okay, this data, and I will go to the same non-parametric test and go to the runs test, and I am keeping everything intact, I am just trying to check. Now, if you see, now what has been done here and what is the difference between the two? If you look at the two values here, what did I do? I converted some of the 1s to zeros. That means what? The 1 was a case of a defective item and the 0 was a good item. So, what I did, by doing a large stretch of values, I took it as a without any break. So, the number of occurrences I have reduced now, the number of occurrences of the groups I have reduced. So, how many groups are there now? 1, 2, 3, 4, then you have, let us say 4, then 5, 6, 7, 8, 9, 10. So, earlier you had something 16, now I have brought it to 10. So, 10 runs I have. So, when the number of runs has been reduced, automatically the significance, the chance of getting a significant value is becoming higher. So, too many runs or too few runs both create a chance of accepting the alternate hypothesis. Okay. So, this is what is the runs test. Okay. So, now we will do one more test, which is the rank correlation test. So, this test is basically a test of correlation between two variables or which are measured in a ordinal scale, right, in a ranked way. So, what is this rank correlation? What is correlation, by the way? Correlation talks about the strength of two values, the strength of the relationship of two variables. Okay. So, if the two variables have a very strong relationship, so we say a very strong positive relationship, or it could be a very strong negative relationship, or it could be a very poor relationship also sometimes if it is not very strongly related. So, let us say sometimes we say the height of a person and the weight of a person is a very strong correlation. If he is more tall, then that naturally there is a chance that the weight of the person also might be higher. Similarly, one interesting observation has been seen that people who wear, let us say, watches on the right hand, are more artistic in nature. So, the degree of being artistic in nature and the wearing of a watch in the right hand are highly correlated. So, such kind of events are very important in life to understand which two variables are correlated. To do this, if your data is in a normal data, then there is no issue, we use a Pearson's correlation, right. So, but if the data is not in a continuous way, so we in that case is following a non-parametric distribution or a distribution free data, then we say it is a rank correlation, or we say the Spearman's correlation, right. So, let us see, the Pearson product moment correlation coefficient is a measure of the linear association between two variables using quantitative data. But in this section we will provide a correlation measure of association between two variables when ordinal or rank order data are available. So, when the data is available in a ordinal or a rank order manner, in such a condition we will use the rank order correlation or the Spearman's correlation. So, the Spearman's rank correlation coefficient has been developed for this purpose. Okay. Now, this is the formula. So, as you know, correlation is always given by the small r is equal to 1 minus 6 summation of d square, where d is nothing but the difference in the ranks, divided by n into n square plus 1, where n being the number of observations in the sample. So, let us see what is saying, xi is the rank of the observation I with respect to the first variable, y is the rank of the observation I, same I, right, with respect to the second variable, and d is xi minus yi. Let us solve a problem, right. So, we will understand. So, this is a problem. A company wants to determine whether individuals who had a greater potential at the time of employment turn out to have higher sales records. Did you understand what does it mean? A person, when we recruit somebody or a company recruits somebody, during the interview they think that this person is a very potential, has a large potential or a huge potential, and he will do a better job in comparison to maybe some of the others, right. So, this thought, is it actually going well or it is not. So, they want to determine whether individuals who had a greater potential during the interview or the employment, do they actually turn out to have a higher sales record. To investigate this, the personnel director reviewed the original job interview reports, academic records and letters of recommendation for 10 current members of the sales force. After the review, the director ranked the 10 individuals in terms of their potential success at the time of employment assigned to the individual, right, and who had the most potential, the rank of 1. So, the best performer as per at that time during the interview or the employment when he was selected was given 1, and obviously the rank goes down till 10 if there are 10 people. Then these 10 people's data was collected on the actual sales that they have made. This sales people's sales record has been collected for the first 2 years of employment. On the basis of the actual sales record, a second ranking has been done on basis of the sales performance. So, let us see the next table. So, what it is saying that these are sales people A, B, C, D, E, F, G, H, I, J. So, 10 people are there, right, and the ranking during the as per their potential is, so D was the given the first rank, second rank was given to A, right, third rank was given to F, fourth rank was given to B, fifth rank was given to J, and so on, right, and till you get the last rank was given to G. Okay. After 2 years the sales data was taken and then there was again a ranking done. So, this time the first rank has been given to A, right, who earlier as per potential had got the second rank, right. The second rank has been given to J, who had earlier got as per potential the fifth rank. So, this also tells you whether the recruiter were also correct in their thinking process or not when they recruited the salesperson. Okay. The third was the one who is B and who had got a 4th rank. So, it goes on. Now, who is the 10th? The 10th is the person who was earlier also 10th in terms of potential, right. So, this is the ranking in terms of the 2-year cells, and this is the ranking in terms of the potential while which was assigned during the joining. So, how do you compute the Spearman's correlation for the data? Right, look at this, we first compute the difference. From here you should see, we first compute the difference between the 2 ranks. So, this time the rank of the potential was, go back, let us see. So, this was 2nd rank and the same person gets a 1 rank, here 4 and 3, let us say. So, 2 and 1. So, di is xi minus yi, right. So, this is 1, correct, 2 minus 1, 4 minus 3 1, right, 7 minus 5 2, 1 minus 6 minus 5, 6 minus 7 goes on, right. So, if you look at it, you got a di. So, this is the difference in the rankings as per the potential and as per the actual cells. Okay. Now, we take the di square, right. So, this is 1 1, 2 is 4, this is 25, this is 1 1, 0 1 1 9, and the summation of the di square is 44. So, R the Spearman's correlation of this S is Spearman's correlation, right. So, R S is equal to 1 minus 6 summation d I square divided by n into n square plus 1. So, this is equal to 1 minus 6 into 44, right. So, 44 divided by n is 10. So, this is 10, right. 10 square is obviously 100 minus 1. So, this gives us a value of. So, the correlation, the Spearman's correlation coefficient value for this case is 0.733, which is strong, right. So, the more it is close to 1, we can say it is a strong correlation. So, it ranges between -1 to +1. So, -1 is extremely strong but negative, +1 is extremely strong but positive, and 0 is hardly any relationship. So, the Spearman rank correlation coefficient ranges from -1 to +1 like any correlation coefficient, and its interpretation is similar to the Pearson product moment correlation. A rank correlation coefficient near 1, which is in this case, indicates a strong positive association between the ranks for the 2 variables, while a rank correlation coefficient near -1 indicates a strong negative association. So, in this case, in this example, RS is equal to 0.733, which indicates a positive correlation between the ranks based on potential and the ranks based on sales performance. So, now the director can understand whether there is a relationship between the potential that was envisaged or the gauged during the time of the selection and actually the way they are performing. Is there a strong correlation? Now, yes, there is a strong correlation, and this strong correlation is almost 73%, right. So, based on sales, individuals who ranked higher in potential, at the time of employment tended to rank higher in the 2-year sales performance. Let us go to have a visual look also. So, so this was given 2 and the sales rank was 1. So, this close 4 3 close 7 5 slight difference 1 6, there is an absolute change in this case, right. So, he was thought to be 1, but he turned out to be the 6th person in his sales performance. 6 7 again close, 3 4 close, 10 there is no difference at all, 9 8 8 9 5 2, this is again difference. So, this is the highest difference you can see, and this is the second highest. Otherwise, more or less the other 8 they are very close to what they were expected to do, right. So, rank correlation at this point, we may want to use the sample rank correlation, this value RS, to make an inference about the population rank correlation coefficient. So, to do this, what is the inference we want to do? That there is no difference or there is a strong correlation, right. So, PS is 0, right, and my alternative hypothesis is that the rank correlation population correlation coefficient is not equal to 0. Under this assumption, the null hypothesis is true and the population rank correlation coefficient is 0, right. What is saying? This is, please understand, under the assumption that the null hypothesis is true and the population rank correlation coefficient is 0, the following sampling distribution is used. Now, what is saying? In this case, the mean stands at 0 and the standard deviation is calculated by root over of 1 by n minus 1. So, n is let us say greater than or equal to 10. So, let us take it 10 this time. So, 1 by 10 minus 1, right. So, that is equal to 1 by 3 1 by 9. So, that is equal to 1 by 3. So, that is equal to 0.33. Okay. The sample rank correlation coefficient for cell's potential and cell's performance is 0.733 we had calculated. Using the above equations we have mu is equal to 0 and standard deviation is equal to 0.333 which we calculated. So, now the z is equal to r minus mu. So, mu is, if you go back to the hypothesis, what is saying that the hypothesis P s is equal to 0, right. So, this is what we are talking about is 0. So, and standard deviation is this. So, the z value is coming to 2.2. So, now using the standard normal probability table and z is equal to 2.2, we find the two tailed p value is 1 minus 1.9, this is the area under the curve 0.9 is this much, right. So, with a 5% level of significance, the p value is less than or equal to alpha. Thus, so in this case is less than, right. So, this is 0.02. We reject the null hypothesis that the population rank correlation coefficient is 0. The test results show that there is a significant relationship rank correlation between potential at the time of employment and actual sales performance. Had it been 0, that means you would have said there is no relationship, right. There is no relationship, they are it is same, what it was assumed to be, it is more or less the same, right. So, but in this case, since there is a difference, we say the test result shows that significant rank correlation between potential at the time of employment and the actual performance, there is a significant difference. Okay. So, this is the Spearman's correlation coefficient which we have understood and how important it is, we have seen that. Let me show you how to conduct this on a, let us say I have created a data set for you. Now, let us say this is the data of a students, right. How many students are there? 30 students, right. See, please understand, I am creating small data sets, but if you increase the data set, sometimes what looks insignificant to you will become significant. So, sample size should be as high as possible, right. So, now I want to see whether students who brought English, the marks in English, and the same students brought some marks in mathematics, is there any relationship between the marks that they have received in English and the marks that they have received in maths. So, in this case we will say the PS is equal to 0, my null hypothesis is PS is equal to 0 or the correlation, population correlation is 0, right. That means there is no correlation, but actually heart of heart we want that there should be some strong correlation, negative or positive, that is immaterial, because that is rather a good thing to know whether it is a negative relationship or a positive relationship. So, let us see how to conduct this test. So, go to analyze, go to correlation and then bivariate. Okay. So, let us take these two, right, and now our data we are saying is a non-normal data. So, since it is a non-normal data, the general by default it is given a Pearson, but we do not want the Pearson because our data is in a, we want to check in a ranked form, right. So, let us take the Spearman's correlation, right. So, when you take the Spearman's correlation, it automatically takes in for a ranking, right, and is thus then tests the subject. So, let us go to the output. Now, in this case, if you see the non-parametric correlation, what it is saying, English mark and your maths mark, is there a strong correlation? Now, yes, there is. English and maths, the relationship is 0.589, which is the correlation is significant and is found to be significant at the 0.01 level, right, 0.01 level, which is and it is a two tailed test, right. So, it could we said it is a two tailed because -1 +1, so it can go on both sides. So, we do not know which side it will be going. So, anyway, so we found that the Spearman's correlation coefficient in this case is giving us a clear indication that there is some strong correlation between the marks scored between the English among the students for their English and maths. Now, whether it is what kind of a relationship that can be checked, but then we are saying there is a significant relationship. So, right. So, this is what we can understand that means what, if somebody is scoring good in, let us say, English, he can be scoring good in maths also, right. Why? Because he is a good student, or it could be possible that a student who is good in English, his one side, his language processing part in the brain is better than the mathematical part. So, if he is doing good in English, he should not be doing good in maths. So, there are two logics, right. So, we can now which logic is coming true, that can be checked, but here we are sure that there exists a strong correlation between the two values. Okay. So, this is what we have done in the rank correlation, and in the next I will tell you about one more test called the Wilcoxon test, right. So, this test is a similar test which is again a non-parametric test, and is used for analyzing data from a matched sample experiment. So, there are two, let us say the Wilcoxon test is a very powerful test. This test uses quantitative data, but does not require the assumption that the differences between the paired observations are normally distributed. The Wilcoxon signed rank test, as I had earlier said to you, between the difference, there is a difference, the sign test which we had done earlier, I had said it is not a powerful test, right. On the other hand, the signed rank test, this Wilcoxon signed rank test is a very powerful test, right. You use for that are at least ordinal in scaling. So, that means you have measured the data in a ordinal scale. So, when a researcher wants to analyze two sets of data obtained from the same individuals, the appropriate test to apply is a related t test. So, we say it is like a paired sample, paired t test. So, for example, the case of blood pressure, when you check the blood pressure or you check the efficacy of a food habit for people who are exercising, if they take more protein, what happens to their stamina or something. However, when there is an extreme violation of the normality assumption, the Wilcoxon signed rank test can be used, obviously. So, it is used against the paired test which you use in a normally distributed data. The assumption is the scale of measurement within each pair must be at least ordinal in nature. The differences in scores must also constitute an ordinal scale. Okay. Now, let us take this. So, there are two methods, right. So, there are some workers who have been taken. Consider a manufacturing unit that is attempting to determine whether two production methods differ in terms of task completion. There are two production methods A, B. Whether these two methods they take different time, right, in completing the job. Using a matched samples experimental design, 11 randomly selected workers completed the production task 2 times, for one with the A method, one with the B. The production method that the worker used first was randomly selected, right. The completion times for the two methods and the differences between the completion times are shown. So, the first when they took, so first one took 10.2, in the B method 9.5, 9.6, 9.8, third 9.2, it goes on. So, and the difference has been measured, if you can see the difference, how much difference of time has come when they are using between the two methods. So, A minus B is equal to this what we have got. Let us say a positive difference indicates that the method A required more time, a negative difference indicates that the method B required more time. Obviously, do the data indicate that the two production methods differ significantly in terms of completion times? If we assume that the differences have a symmetric distribution, but not necessarily a normal distribution, the Wilcoxon test applies. Okay. Now, what he is saying is we will use the Wilcoxon signed rank test for the difference between the median completion times. I had told you several times that in a non-parametric test we are more interested in the median and not the mean, right. So, the two production methods, the hypotheses are the median for method A minus the median for method B is equal to 0, or that means the median for method A is equal to the median for method B. In the alternate hypothesis, we say the median for method A minus the median for method B is not equal to 0. So, this might be more, sometimes this might be less, or this might be less, this might be more, correct, whichever. If H0 cannot be rejected, we will not be able to conclude that the median completion times are different. Obviously, that is how the null hypothesis is to be understood. However, if H0 is rejected, we will conclude that the mediation completion times are different, and this is what is of interest to the researcher. So, the level of significance used is 0.5, right. So, what you do is the first step in the Wilcoxon test is to discard the difference of 0 for worker 8, like look at the worker 8. So, there is a worker 8 has got a difference of 0 because it is same, right. So, we need to discard it and then compute the absolute value of the differences for the remaining 10 workers. So, next we rank these absolute differences from lowest to highest because you want an ordinal scale, right. The smallest absolute difference of 0.1 for worker 7 is rank 1. So, what is saying? The smallest absolute difference of 0.1 for worker 7 is the rank 1. So, worker 7 has a difference of, so that means the both the methods are taking almost the same time, right. The second smallest of 0.2 is 2 and it goes on till you get the highest difference, and that is the 10th rank, right. The tied absolute differences of 0.4 for workers 3 and 5 are assigned the average rank of 3.5. This is how you do. So, there are two, let us see. So, 3 and 5. So, 0.4 here and 0.4 here, correct. So, absolute, if you see the absolute value is, so for 3 and 5. So, what you do is 3 plus 5, right. So, since not 3 plus 5. So, 3 and 5 the absolute difference of 0.4 for workers 3 and 5 are assigned the average rank of 3.5, yes. Why? Because if you can see, go back, let us go to the front one. So, the rank you see 1, 2, right. So, lowest, then 3 is, you do not have 3. So, you have 2 same. So, what you have done is instead of 3 you have given as a rank of 3.5, 3.5, right. Then 4 you do not have, right. So, then we will go to 3.5, 3.5, then the next is you are going to 5th, where is 5? So, 5 is also, there is some similarity I believe, yes, okay, this is also 0.5, this is also 0.5, the difference. So, that means, so after 3.5 the next is 5.5. So, 5.5 here, 5.5 here. So, the next is after this is the 7th, okay, then 8th, then 9th, then 10th. So, this is how the rank is to be made, okay. So, after these ranks are made, the negative and the positive values are taken, the sum of the positive signed ranks is T is equal to 49.5. If you add up this total, it becomes 49.5. So, if you see what it is saying, the difference for worker 1 was positive 0.7 and the rank of the absolute difference was 8, this is 1, right. For the rank for worker 1 is shown as a positive rank in column 6. Thus, difference for worker 2 was a negative 0.2, this one, and the rank of the absolute differences was positive 2, right. And thus the rank of the worker 2 is shown as a negative sign of a rank 2. So, this is what it is saying is, so this gets a negative sign rank 2, right. So, okay, this is differences 0.2 absolute difference and this tell you okay. So, continue this process generates the negative and positive sign. So, the scale of measurement within each pair must be ordinal in nature, and it basically uses a ordinal scale, right. So, this is the example. So, what we will do is I have worked on this example. So, we will take this example in the next lecture and we will work on it how the difference of two methods, right, has been taken to understand the effectiveness of the workers, right, and how the Wilcoxon rank test has been used for this purpose, right. We will stop it here. Thank you so much.